Hi everyone. To wrap up chapter 7, we're going to take a look at a couple of applications of logs and exponentials, and probably the most common one is compounding interest. So let's talk about interest a little bit. Basically, whenever anybody either borrows or loans money, they are either going to pay or earn interest. If you borrow the money, you pay interest. If you loan money, you earn interest. Now, whenever that interest is calculated, we call it compounding interest. And there's a lot of different ways to do it. So basically, like for our example, let's say you put some money into a savings account in a bank. You might earn 2% interest or 3% interest, depending on what the rates are. So you put your money in, and the longer you leave it there, you start earning little bits of interest on it. So when it comes to compounding or calculating interest, it can be done a lot of different ways. Basically, what we're talking about is how often the interest is compounded or calculated. So the first one, which is usually called simple interest, would be yearly or one time per year. So that would be like you take some money, maybe you have a couple $100, you put it into a savings account at 2% interest. The bank holds onto your money for the entire year, and at the end of the year, they just pay you 2% of whatever you put in there. Now, another way of compounding interest would be monthly. So maybe they're going to pay you at the end of every month instead of every year. Now they're still paying you the same amount. They're still paying you 2% interest. But what they're doing is they are giving you 1/12 of that amount each month, since there are 12 months in a year. Weekly, maybe interest is compounded at the end of every week. So they give you, there are 52 weeks in a year. So they give you 1/52, 1/52 of the total amount of interest that you earned at the end of each week. Daily, etc. Daily would be 365. I could say quarterly, maybe once at the end of every 3 months, they pay you 1/4 of your interest. So basically, compounding interest just depends on how often it's paid out. Now, in the end, you're still earning 2% per year, but they're paying it out either just the whole amount at the end of the year or a little bit at a time spaced out throughout the year. So here's our interest formula. I'm sure you've seen it before. It's a common one. It's a fairly complicated one. We have I equals P times 1 plus R over N to the NT power. So it's fairly complex. There's also 5 different things in there. There's I, P, R, N, and T. So before we move on, let's go through each of those variables and talk about what they mean so we're real clear on that. So the first one is I, and I stands for interest, but it's a little bit tricky because what it actually means is the amount of money in the account after interest is compounded. So for example, let's say you put $100 in the bank and you earn $5 in interest over a certain amount of time. I would actually equal 105, not 5. So it's not the amount of interest you earned, it's the amount you have after you've earned interest. Now, P stands for principal, which is a financial term, which means initial amount invested. So if you go back to that little example I just made up a second ago, P would be 100, that's your initial amount. I would be 105, that's the amount you have after you've earned interest. R stands for rate, or interest rate. Make sure you put it as a decimal. So you turn a percent into a decimal by moving the decimal place over twice. So for example, I gave you an example. I said if you're earning 5% interest, what you would use for R in the equation is 0.05. If you just put the number 5 in, it actually means 500% interest, and your answer is going to be way off, not even close. And then N is what I talked to you guys about a couple slides ago. N is the number of times interest is compounded per year. So if it says in the question we're compounding yearly, N equals 1. If it says we're compounding daily, N equals 365, because there's 365 days per year, and that's how many times you're compounding. And then I gave you the numbers before. If N was monthly, you'd use 12. If n is weekly, use 52. So basically that's what n is. It's how many times you are compounding interest per year. I actually didn't type it in. T is time, and it's measured in years, always. So it's a very simple variable to work with. Just remember that even if it says monthly or daily, T is still measured in years. All right, so here's our first example. We have $100 in a savings account. It pays 2.25% annual interest, and it's compounded yearly. How much would we have after 10 years? So we have $100, we put it into a savings account, we're earning 2.25% interest, compounded yearly, one time per year, and we want to figure out how much is there after 10 years. So the equation I'm going to use is the only equation we have. I equals P times 1 plus R over N to the NT. And what I'm going to do, I'm going to go off to the side and go through the problem and just assign variables to each number. So basically it says you have $100 in an account. That's our initial amount. That's what we call P. So P is 100 for this problem. The account pays 2.25% annual interest. That's R. But remember, move the decimal place twice. It's 0.0225. If you only move the decimal once, if you put like 0.225, you're saying 22.5% interest, and again, your answer will be way, way off. Then in parentheses, it says we are compounding yearly. Yearly means one time per year. That's n. So n is 1 for this question. And how much would we have after 10 years? That's t. T equals 10 years. So basically, when you have an equation that has 5 variables like ours does, what I'm going to do, in fact, the only thing I can do is give you 4 of them and ask you to find the 5th one. And that's what I did. I gave you P, R, N, and T, and I said, how much would you have after 10 years? That's what I is. So I'm basically saying find I. Now that makes it easy because the equation is already in I equals 4. So I'm just going to put all the numbers in. P is 100. We have 1 plus R, which is 0.0225 over N, which is 1. And then we are going to raise it to the N, which is 1 times 10. Now at this point, it's a calculator question. I'm not going to have you guys try to do a bunch of this by hand. Once you get to the point where you're ready to just type it into a calculator, just do that. So I'll pause, do that on the calculator, get the answer, and come right back. All right, so the answer I got for this one is $124.92. That's how much you have after 10 years, which means basically we already started with 100. So if you subtract off the 100, what it's saying is we earned $24.92 in interest. All right, so what I'm going to do for a part B for this question is I'm going to make a tiny change to it. Let's see what happens. See if there's any difference in how often you compound. So let's take the same question, which means I'm still going to do my principal is 100. I'm still going to do the rate is 0.0225. Let's see here. Time is still 10, but what I'm changing is n. So instead of compounding yearly, one time per year, I'm going to compound monthly, which is 12 times per year. So let's go ahead and do that and see what we come up with. Same formula, I equals P times 1 plus R over N to the NT. And let's put our numbers in again. So this time we have 100 times 1 plus 0.0225 over, this time instead of over 1, it's over 12. And then it is going to be raised to the 12 times 10 power. So it's the exact same question, but n shows up twice in the formula. Once in the R over N and once in the NT, in the exponent. So just change those 1s to 12s, crank it into a calculator, and again, see what you get. So I'll be right back with the answer. Okay, this time I got about 125.21. So basically it was about 30 cents more than we earned last time. Last time we got 124.92. So we earned a tiny, over 10 years it's 30 cents. It's not much, but it is a tiny bit more. Let's do one more. Let's compound a little bit faster. Let's compound daily and see if it makes a difference again. So again, I'm leaving most of the stuff the same. The principal is 100. The rate is 0.0225. Time is 10 years. But this time, if we're compounding daily or every single day, that's 365 times per year. So that's what's going to change this time. So same formula. This time when I plug in my numbers, I'll still have 100 here. I'll have 1 plus 0.0225 over 365, all to the 365 times 10 power. And I'll be back with the answer again. All right, and this time I got 125.23. 2 cents more over 10 years, so almost nothing, but it isn't nothing, it's a tiny bit more. So basically what we're seeing right here is that the more often you compound interest, the more interest is earned. And sometimes it's only a tiny bit, like the difference between monthly and daily was 2 cents over a 10-year investment. That's almost nothing, but it is more, a tiny bit. And here's the reason. Basically, we're earning the same amount of interest, but if you're putting it into the account more often, you're earning interest on the money that you put in there. So my first example, we put our $100 in, we earned interest, and at the end of the year we said, how much is there? But the second example, we put our $100 in there. At the end of the first month, we put a little bit more in there. So on that second month, we were actually, instead of earning interest on $100, we were earning interest on like $100.20 or something. And then on the second month or on the third month, we were earning a little bit more. So you're earning interest on the interest. So basically what it comes down to is the more often you compound interest, the more you're going to make, just by little bits, not by a ton. Now that leads to really the main type of compounding interest, and that's this theoretical method called compounding continuously. And it's actually a limit concept, which is good because we've been learning limits this year. So if n is the number of times that you're compounding interest per year, and as n gets bigger, the amount of interest gets bigger, we kind of take the limit as n approaches infinity, and we say, well, what happens if you're just always compounding interest? And what it does is it gives us an easier formula to use. So this is the other compounding interest formula. It's I equals P e to the RT. It has the e to the x in there, that's what the e is. But there's no n in this formula. And that makes the formula a lot easier to work with. So when you're compounding continuously, you get to use this formula and it's actually much easier. Now remember, the word continuously is the key. You only use this formula, P e to the RT, sometimes people call it the PERT formula, but you only use P e to the RT if it says in the problem that you're compounding continuously. If it says anything else, daily, monthly, yearly, quarterly, weekly, whatever, you have to use that first formula. So let's do one more part. This is our same example, $100, 2.5% interest, 10 years, but this time interest is compounded continuously. And as soon as you see that word continuously, you immediately want to start with this formula, P e to the RT. So there's no n in this problem. When you go to list your variables, it's the same as before. P is 100, R is 0.0225, T is 10 years. But see, because we're compounding continuously, there's no n in this problem. So you're not going to use that first equation that has the n in it. You're going to use the easier equation. So let's answer the question. P is 100, R is 0.0225, and T is 10. And it's a calculator question again. So let me get that answer and I'll be right back. And it basically comes out to the same answer as daily. We get $125.23. That's a dollar sign right there. The difference was what came after the decimal. Like when I did daily, I got 125.230, and now I'm getting 125.232. So it is a tiny bit bigger here, like after the penny, which with $100 doesn't make a difference. But if you're a hedge fund manager investing billions of dollars, then yeah, that is going to make a difference. So yes, the concept here is the more often that you compound, the more you're going to make by little bits. But what you really want to know is when to use this formula. So remember, the key is if you see the word continuously, this is your formula. If you see anything else, compounded yearly, monthly, whatever, you got to use that other formula. All right, I'm going to do one more part to this example because so far everything we've done has been like just plug in numbers and type it into a calculator. And I do want to show you that that's not every single question. So as part, I called it part B, it's actually more like part E. Part E for this example, same situation. While you're compounding continuously, starting with $150, how long would it take before you had exactly $150? Starting with 100. So same thing as before. Our P is 100. We're starting with $100. Same rate because we're just continuing our example, 0.0225. This time we don't know what time is. T equals question mark. That's what I'm asking you this time. How long does it take before you reach $150? That's I. Basically, I'm saying how long until you have $150 in your account, and that's exactly what I is. So what I've done is I've flipped what I'm asking you. There's four variables in the PE to the RT equation. I've given you 3 and asked you to find the 4th one. But so far, all I've done is given you P, R, and T and asked you to just crank it into a calculator. Right now, we're going to have to do some solving. So let's start with it. Now, we are compounding continuously again. So let's start with PE to the RT. And see, this time when I go to plug numbers in, the 150 is over here. P is 100. Let's see, R is 0.0225. And then T is T. That's what I'm solving for. So this is not just to crank it into your calculator and give me an answer one. This is a solve for T question. So what we have is an exponential equation. We just finished talking about these. Step 1 is to isolate it. So I'm going to divide both sides by 100 because I want to isolate that e to the x function. So 150 divided by 100 is 1.5. And then we get e to the 0.0225t. Now, we have our e to the x function isolated. Step 2 is to cancel it. So I'm going to take the natural log of both sides. And what I get is the natural log of 1.5 equals, now remember, natural log and e to the x cancel each other out, so you just get 0.0225t. We're one step away from being done. Divide both sides by 0.0225 to cancel that, and that's going to be your answer. See, now is when you crank it into a calculator. So we had to do some work first. Eventually, once we've solved for t, we are going to have to use a calculator on these. These are not going to be like do it in your head type questions. But let me go ahead and do the calculator work, and I will be right back for the last time. All right, so what I get is about 18.02. And remember, that's time, so that's measured in years. So basically what we figured out, let's say you had $150, or you start with $100, and your goal is to reach $150. If you're earning 2.25% interest on your savings account, it's going to take you 18 years, tiny bit over 18 years to do that. And that's just an example of how, remember, interest questions are not always just here's some numbers, type it into a calculator. We are solving log and exponential equations just like we did in 7.4. Last thing before you go, you're going to have some questions today in the homework about doubling time or tripling time. That's exactly what it sounds like. So if you look at the little green box there, it says if you're asked what is the doubling time at this interest rate, it means how long does it take to double your money. So you could, it doesn't matter what you start with. You could start with 100 and end with 200. You could start with 1 million and end with 2 million. It actually is the same no matter what the starting amount is. So when you get to the doubling or tripling time questions, just make up a number. You can start with $1 and end with $2, or you can start with 1 billion and end with 2 billion. It doesn't matter. Same with tripling. You can start with 100 and end with 300 if you want. All right, that's it for today.